Hi, I'm Anusua, and I am a research scientist in the AI for Good research lab in Microsoft. And today I'm going to talk about how we are using computer vision and NLP techniques um, for healthcare during pandemic. A little bit about our Microsoft mission. We empower every person and organization on the planet to achieve more. And this is basically the very core of our lab, the very principle that we believe in. That's how we try to democratize applications of AI for the good of the society. We have different pillars that we focus on: AI for accessibility, AI for Earth, AI for humanitarian action, and AI for cultural heritage. AI for Health is another vertical which we have launched and feel very passionately about, especially with last year with the advent of COVID-19. We have all become very aware like how health and information go hand in hand, and how important it is to have access to the right information to take the right step to mitigate the problems arising in healthcare. Health is a global issue, especially in COVID-19 last year. With the community spread of the disease, it has been more firmly established. So technology's role is advancing research in this area, democratizing the data, protecting against health crisis, and improving access to care for underserved populations. Our Air for Health vertical is a $60 million 5-year philanthropic grant based program where we try to empower researchers and organizations with AI to advance the health of people and communities around the world. The way that we work is basically we provide grants, Azure grants, to our partners, and we are providing for Azure computing and AI access to Microsoft's top data and research scientists like myself and my team, and the technology expertise and resources all over. The focus areas are quest for discovery, where we are accelerating the medical research to advance the prevention, diagnosis, and treatment of certain diseases. Providing global health insights, where we increase our shared understanding of the mortality and the longevity of to protect against the global health crisis, and the health equity to improve the access of care for underserved populations. There are a number of health partners and grantees that we work on. I'm going to pick up a couple of use cases, and I'm going to do some deep dive to show you how we are working with such organizations to apply computer vision and natural language processing to get more insight into the disease. So we're working with the Novartis Foundation to eliminate leprosy. Around 200,000 new cases are diagnosed yearly. A yearly diagnosis helps limit the disease transmission. Developing AI-enabled digital tool to recognize leprosy lesions could be of immense help to the healthcare workers who are working at the grassroots level. This kind of tools would enable referral to healthcare professionals for early diagnosis. This kind of specialists are really hard to reach. Whereas in remote villages in India or in Brazil, it's really hard to get such leprosy specialists. If we can create certain type of telemedicine tools where the the volunteer workers or the health camp workers are able to capture the images and send it over to the specialist through cloud and technology, then that basically is a success in my opinion. So a little bit about our project from Novartis Foundation.
Today, there are over 200,000 patients with leprosy diagnosed every year. Leprosy comes with an enormous stigma. People lose their jobs, lose their families, and are very afraid to seek healthcare in time. If you catch it in the stage of a skin lesion, you can cure the person. The partnership with Microsoft AI for Health will help us to accelerate diagnosis of leprosy. We are teaching an AI algorithm to recognize leprosy in an image of a skin lesion. We hope that this digital solution will help us also map where hotspots are.
If you have AI embedded in the phone, it can actually detect and mark the region and automatically say the potential for being a leprosy condition, so we can help patients to get to the right experts at the right time. It's the symbiotic relationship between the human and machine that actually brings the magic of AI to medicine in a meaningful way. If you can help a child to be healthy and happy, that means everything. And that's why we do what we do.
Thank you for your attention. So the goal, as you saw, is basically taking some neural networks and using images to train the model, basically an application of computer vision, and where you're trying to get a large leprosy data set using clinical lesion images. But the major thing that we are not seeing in this solution or in the video that you saw is basically the work that goes in the back end. How are you even selecting this kind of images? We are actually using tons of metadata and patient information, and here enters the NLP. Before even deciding which images we can choose to train a computer vision model, we have to figure out which are the images we can actually choose, and that is based on the decision from the patient information which is coming in. To create this kind of leprosy data set, we collaborated with local investigation from Oswaldo Cruz Foundation, Veracruz in Brazil. They were collecting images with each lesion annotated, so which is the computer vision part of it. Along with that, we were getting a ton of metadata for each lesion, for example, measurements. And we are also getting the patient information. For example, like what is the demographic of the patient? What are the underlying conditions they're coming with? What are the symptoms? Those kind of information are extremely important when you're trying to build any kind of model for detection. So the metadata, as you can imagine, because it's being collected from a very global healthcare workers on a very grassroots level, it's basically a handheld, hand filled out form. It's nothing digital. You kind of enter the patient number, the study ID, you kind of include all your types, which is like all the medical metadata, the phenotypes that you're interested in, right? And then you kind of work with, okay, what are the symptoms? Do you have hair loss? What are the white dots, white areas? If there is itching or not, if there's sensory loss or not. So it is painful, asymptomatic, those kind of basically information are extremely important to figure out even before you can go to train the computer vision models. So one of the things that we actually do is basically use form recognizer.
You train an AI model to detect and extract data from your own documents. The sample labeling tool allows you to manually label your training data beforehand. This results in better performing models and can produce models that work with complex forms. First, create a new project and enter a name. You'll need to create a connection to the Azure Blob storage container where you've uploaded your forms. Go to the Connections tab and enter the required information. You can get the SAS URI for your container using Azure Storage Explorer. Next, return to the Home tab and fill in your connection information, along with your form recognizer subscription key and endpoint URL. Then, go to the Tags editor to begin labeling your forms. Create your own tags, and then select bodies of text and apply your tags.
So as you can see here with this kind of form recognizer API, the handheld form which I was showing you for the leprosy project, we went ahead and kind of started selecting and saying, okay, this is a patient symptom. This is a patient, this is basically a patient, a way of like tagging a patient if the patient is having hair loss or not. So those were some of the tags that we created, which kind of started acting as labels for our images, so that we can start choosing those metadata along when we were trying to create the computer vision model.
You don't need to tag table data. This will be detected automatically. When you're done tagging all of your training documents, go to the Train tab and begin training. The ID of the train model is returned. You can use this model with the Form Recognizer API to extract data from your documents. To test your model, load a sample document, go to the Analyze tab, and run a prediction. The model will extract data from the fields you've tagged and will return a confidence score for each field.
It will also extract any table data. Your model is now trained and ready to go.
So you saw like how we are using form recognizer to extract such metadata, and then basically using a combination of computer vision and NLP to train such medical models. If you're just using images randomly, it might not give you the right insight, but a combination of the computer vision and the NLP data extraction kind of leads you to create a better model. One another such example that I wanted to take about was the Cascadia Data Alliance, which we had. This is basically for accelerating cancer research collaboration across borders. The cancer research data currently is siloed within institutions. This initiative aims to establish data collaboration across the region. There are different like regional rules. For example, if you're working with some institution in EU, they have their own rules around GDPR. So we are applying something called the digital privacy. So basically, differential privacy is a key asset to collaboration, allowing researchers to access of data while protecting privacy of individuals. This is a way in which you are kind of providing the growth statistics without letting out any kind of personally identifiable information, which is extremely important in healthcare, right? So that if I'm applying differential privacy, it will be very hard for any kind of adversarial attacker to come in and figure out who is the person with blue eyes, black hair living in this zip code. So it's a way to kind of secure your data, that we have gone with. Another one such example that I wanted to take and do a deep dive on was on a project we are doing with Fred Hutch called Quidbot. This is a personalized therapy chatbot for helping to quit smoking. This is a part of a 5-year NIH grant where we conduct a clinical trial, and we're going to launch the clinical trial sometime towards the end of this year. Fred Hutch has already worked on a Quidbot version 1, but it was basically a rule-based model, not conversational. In this particular NIH grant that we received, we have worked with Fred Hutch to make the model more personalized and more engaging, and have a more empathetic conversation around. So the data set that we built with them was using therapist call logs. So basically, we had some kind of call logs, a transcript of those call logs were generated, and we used some Quidbot V1 version chat logs. We manually curated question answer pairs from experts on how to quit smoking, common chit chat, and COVID-19 related questions for quitting smoking, because you might realize, because if you're getting lonely, you're getting depressed, you might resume smoking. And quitting smoking is extremely important, especially in cancer patients. Otherwise, your therapies are not working properly. So from that, we also started using data collection using, diary studies on prolific users. These are simulated users where you are kind of doing some kind of data collection from certain demographics of people. As you can see, we are running several different models in this particular bot. We have some quit values, we have some smoking triggers and time quantity related AI-based models. We have a dispatcher dialog flow, which kind of understands when a question comes into the chat API, in the chat UI, what this question intent is about. Is it a chit chat? Is the person trying to quit smoking? Is it a depression related question? Is it like COVID-19 related question? So it's trying to kind of gauge the intent, and based on that, it's trying to forward it to different types of question-based things. We are trying to use Gpd3 based model, and we retrained the Gpd3 model, fine-tuned it essentially to handle chit chat and smoking quitting, that is smoking trigger based questions. So a little bit about Gpd3. It's the OpenAI's third generation pre-trained transformers. It is a general purpose language algorithm that uses machine learning to translate text, answer questions, and write text predictably. So we're using it for two use cases, essentially. We are running a question answering model where it's not an extraction model, it's a generation model. So it learns about the content and the tone of the question answers that we are giving, and kind of learns how to generate answers. And we also have a text generation model which we run on top of the question answering model, kind of doing a qualitative scoring on the answers generated. So how the Gpd3 works. Gpd3 has 175 billion learning parameters that allow it to perform almost any task assigned to it, making it larger than the second most effective language model from our Microsoft and the Turing NLP algorithm, which is only 17 billion parameters compared to that. So why Gpd3 is super hyped. So why is Gpd3 super hyped? The response is simple. It is the largest model that has been educated. The 175 billion learning parameters outweigh any previous non-sparse language model by 10 times. Gpd3 is used for all tasks without the need for gradient changes or fine-tuning. For our case, we are doing fine-tuning because this will go live on patients, and we want to have a more tighter control over what type of answers we are generating. We do not want to go into any kind of hate speech generation or any kind of we want to control the tone deafness, the gender neutrality. So we kind of try to control for all of those things, kind of applying content moderation, and we fine-tune those models for this particular use case. So Gpd3 can rightly answer any kind of trivia questions. It can predict the final word of the sentences. One of my collaborators from my research lab said that he also started, using Gpd3 to generate a skeletal for its writing paper discussions. So and writing any kind of articles with the human nature from a title is also its forte. So coming on to, with that, I'm going to move into broader COVID-19 related applications that we have been working on. I went into deep dive on computer vision and NLP collaboration. I went into deep dive into differential privacy, how we're making things secure. And I also went into Gpd3, which is the latest state-of-the-art NLP model. But how we have been working to handle the COVID-19 response with this kind of tools and assets that we have developed in our lab is basically something that I want to cover a little bit today. So we started working on COVID sometime back in February 2020, when we are from the state of Washington. So in the state of Washington, we got first hit in America. And so basically, we got very early on data. We started collaborating with China, trying to get a lot of data from them. Till date, we have about 150 grants awarded since the last of April. The length have reduced from months to days, and we to generate, because initial few months were spent on developing models. There are different types of problem sections that we have worked on, mainly to help policymakers make data-driven public health-related and safety-related decisions. Basic scientific research covers about 14% of our investment data and insights. So basically, we power the Johns Hopkins University dashboard that you see on COVID-19, the Washington State Department's dashboard on COVID-19. So basically, we have a treatment and diagnostic section. We kind of collaborate with doctors to work on those. Air for Health COVID-19 data visualizations and powering dashboard that I mentioned, and understanding the progress to zero metric is a way that we came up with to track the process globally. We are part of the White House consortium to battle COVID-19. We worked with several different grantees to work to basically handle. So I'm just going to go over this one particular example, and then basically we can stop after that.
So the COVID Moonshot is a loose collaboration of a number of pharma, academics, research institutes to find a solution to the COVID pandemic. Where UCB believe we can really make an impact in this space is computational drug design.
The UCB technology we applied to tackle this challenge starts with large-scale simulations, and that requires a lot of computing power and a lot of data processing.
We reached out to Microsoft and the AI for Health team. A week after that, we actually started work within the Azure platform. We ran something like 275,000 hours of CPU time across data centers, both in Europe and in the US during this process. Using available UCB resource, it would have taken us something like 6 months. With Microsoft Azure, this has taken us 3 days.
They enabled us to do what we couldn't have imagined to do. The designs coming out of this collaboration with Microsoft Azure team are amongst the front runners right now.
Finding cures, finding the ability to really help is not something which one company can do by themselves. You don't get there alone, you get there together.
So this is one of the examples, how, big cloud computations and, large neural networks can help you get insight from not only just text and images, but also from large genomic sequences. So yeah, with that, I'm gonna end today. I hope you enjoyed our presentation, and if you have any question, I would be available for to answer it. Thank you.